Welcome to the second part of our video on line integrals. In the first part, we've examined some technique corresponding to finding the line integral. Today, we'll be talking more of the intuition behind the technique. What do we actually do when we're finding the line integral? What is the sense behind it? Right, so how do we make sense of this intuitively? Well, recall that the arc length differential in a two-dimensional plane is defined by this formula. Just to refresh your memory, the arc length of a curve is the length of the curve itself. That is, imagine you could straighten the curve you see on the screen here and measure its length. That length is the arc length of the curve. So the arc length differential is, if you may, the instantaneous length, or if you could imagine, the length or width we get after we take an infinitesimally small point-sized segment of the curve. Notice that we can approximate the length at any given interval by applying the Pythagorean theorem. That is, we take the root of the sum of the squares of the change in the x-coordinate and the change in the y-coordinate. So if we can manage to take smaller changes of x and y, we will get a more accurate representation of the length of the interval, as demonstrated here. So how do we get the smallest change in x and y so that we can get an accurate length of the differential? Well, if we let x and y be parametrized by some function of t, then we can take the derivative of it, right? And since the derivative, explored countlessly in calculus classes, gives us the instantaneous change. So for any fixed value of t, we can get an instantaneous change of x and y simply by finding the derivative with respect to t, provided of course that x and y is continuous on the interval in t. So if you need help visualizing, try treating the variable t as some point in time and treat this curve here as the motion drawn out by a particle. So imagine this particle is just allowed to move in your perspective a very quick, or if you could picture it, the smallest instant in time. And so there would be small changes in a particle's x and y coordinate. That smallest change in x and y with respect to time is the derivative of x and y with respect to t. But that is exactly what we need. So we will take the smallest change, the derivatives, and plug it into the Pythagorean formula, and that, it turns out, gives us the formula here. So imagine that the differentials we get here, the super small infinitesimally minute segment of the curve, each would project some value onto some other dimension. Now when I say dimensions, I don't necessarily mean dimensions in space or some esoteric notion of dimensions, such as those discussed in superstring physics, for example. Well, we could debate if they are or should be esoteric or not, but that is not the point of me telling you this. What I'd like to say is that dimensions in our context can be almost about anything, however trivial they may be. You could, for example, say that taking any value from the dimension of the amount of sugar and milk in a cup of coffee will determine or project some value in the dimension of my subjective preference for it. You could talk about the dimension of your company's revenue and its relation to the dimension of your relationship with your boss. You could talk about the dimension of heat, light, sound, the dimension of poker hand-win ratio perhaps. I hope you can pardon my very non-rigorous way of speaking, but I'd just like to emphasize that in our context, the scope of what dimensions can cover is very broad. And it really just translates to the area of study you're focusing on, and it's not strictly restricted to geometry. But we will use geometry to convey the idea of dimensions just because it is more intuitive and more easily visualized. In fact, one of the beauty of mathematics is that we can translate the ideas of geometry like graphs into some other areas like business and physics and music and art and still have the calculations all work out. But let's not get ahead of ourselves here and return to our discussion. So imagine that each differential here projects some value onto some other dimensions, and we will call this value the height, since it's easier to picturize than say temperature. So immediately you can imagine a large amount of thin, infinitesimally thin column strips, which are the products of the differentials, the width of the strip, and the height, the projected value of the curve. And because these column strips are so thin, the sum of all of the strips from some beginning strip A to some strip B would give us the area of this sheet here, right? So more precisely, we say that the definite line integral from A to B gives you the area of this sheet, this 3D curtain you see here. And remember, because we're doing integration here with respect to dt, we need to transform all the functions and the boundary values in terms of t as well. So this function here is actually now a function of functions, since x is now a function of t, y a function of t, and z a function of t. Also note that the boundary values a and b are also now functions of t, or else the integration wouldn't make sense, right? So we will rewrite a and b in terms of t. So that's basically what it means to do line integrals for a curve in 2 dimensions. So now let's extend this idea of the line integral into 3 dimensions. So imagine that this curve here is no longer flat. That is, it now takes some space, as seen here. Well, the idea of the arc length differential still persists here, right? The differential still means the smallest distance between points on the curve, and so we can still make use of the Pythagorean theorem. So like before, what we need now is to find the smallest change in x, the smallest change in y, and the smallest change in z, and finding the distance they produce by plugging their values into the Pythagorean formula. So how do we find the smallest change of the x, y, and z coordinate? Well, similar to the previous case, by parameterizing the x, y, and z coordinate of this curve here and finding the derivative, we've essentially taken the smallest change the coordinates can have, right? So let's plug them into the formula, and we will get something like this. And this, as we've learned in the previous video, is the term ds, right? So by now I hope you understand what it means by saying that ds is equals to this. It just meant the small change of the length of the curve right here. Also note that most often you will see in textbooks that ds is equal to the magnitude of dr over dt. But that is of course essentially the same idea of what we're talking about, right? If you can imagine what r is, well pretend that this curve represents a motion of a particle again. Then r is essentially the position vector of the particle with respect to the origin, right? The position vector. So by taking the derivative, we're essentially finding the velocity of the particle at that particular point. That is, given an instant amount of time, how much that particle would change in relation to its position vector, right? So by taking its magnitude, we would find the instantaneous distance the particle would have run. So that is essentially what we've meant by ds before, right? And in fact, if you do the calculations, you'll find out that the two are both quite the same. So now I'd like you to take a step in your imagination. I'd like you to imagine a 4th dimension. Now remember, we don't have to imagine a 4th dimension in space, unless of course you're eager to. Then maybe you can view that each point in the curve projects into some point in a separate number line. But remember, we don't have to. We can just imagine another area of study we're focusing on. So maybe the dimension of density perhaps, or the dimension of heat, or the dimension of hue. So I'll just go ahead and think of a dimension of a general property P, whatever P you want to think of, as long as P can be real and numerical. So to imagine the line integral, you have to imagine that each differential, each point, possess some property P, and that each value of P depends on the coordinates of the point. So maybe if you're thinking of P as density, then at this point, it will be denser than, say, this point. Or this point will be at about the same density at this point. You get the idea. So like in the previous three-dimensional case, what we mean by line integral is that we get the sum total of the products of the property P of the point and the differential itself from some beginning point to some end point. So if P is the density of the differential, the product would give the point's mass, and the integral would give the total mass of the system. And since this is mathematics, we can still use this idea of density as a visualization aid to visualize line integrals whereby the fourth dimension isn't density, like in terms of profit or temperature or hue. Pretty neat, huh? One thing to note though, since P can be anything, our product of the property P and the point can have a negative value. So if, for example, P is temperature, then if a point is, let's say, a little less than 0 degrees, we will get a negative valued product. So that means line integrals whose values are negative is totally acceptable mathematically. So if you insist on using an analogy of density, you could imagine the property as well well, I imagine the property P as density can have like let's say if this property P is density, then this density can have valence, like say good and evil. That like if at that point that P is positive, then it'll produce some modulus P amount of good mass, and if at that point P is negative, then it will produce modulus P amount of evil mass. So when the same amount of good and evil mass meet, they will annihilate each other, for example. And so the sum total of all of these masses, the line integral, would give this intense, nerdy, epic battle between the good and evil mass, and whoever has a larger value will come out. So that's how I imagine it. But of course, you're the designer of your imagination, so you can think of something else to aid you in your visualization if you wish to. So more precisely, by the line integral, we mean the integral over some curve C of the function P with respect to ds. And since ds is equal to this formula, we can write the whole integral in terms of dt. And so P must be in terms of t, and the boundary values should as well be translated into points in t, that is a and b. Calculating this set of formula is what we mean by finding the line integral. So that is essentially what we do when we say we are calculating the line integral. Right, I hope you've made some sense into maybe something a little confusing at the beginning. And I hope you also realize that it is not as abstract as you might have thought. Well, I hope we've been a help for you. Thank you for watching.